Welcome to lecture 24. In the previous lecture we derived the governing equations for the Josephson junction, which we show to be equivalent to that for a driven and damped pendulum. What we'll do during this lecture is to fully analyze the second order ODE and look at some of its properties. And in particular, what we'll do is we'll introduce a new method of analysis that was first used by Poincaré and lays a very important foundation for analyzing systems in which chaos occurs and in fact distinguishing between systems that are chaotic and not. So this is one of the first sort of more abstract tools that will be introduced with this example. Okay, so the equations that we derived in the rescale time variable is simply, we're going to write them in first order form. So we say let phi prime equals to y, and then we're going to have y prime equals to 1 minus sine of theta plus alpha times y. And we have that both that alpha and I are greater than 0 simply because of the physical constraints, and it's true both of the Josephson junction and of the driven pendulum. And these are the control parameters. They're basically the knobs in the physical system that you can change. In the case of the pendulum, I is simply the driving. So suppose you have a pendulum attached to a string, and at the base of the string you have a little motor or just your finger that you tweak the string to make the pendulum go. Alpha plays the role of the damping in the pendulum. So it basically tells you how much resistance to motion there is at the point that your string is pivoted. And for the Josephson junction, please refer back to the previous lecture as to what I and alpha actually mean. It's a bit more complicated. So what I'm going to do now is simply analyze this. So it's the normal analysis, linear analysis to start. The fixed points from the first equation is that y star is equals to 0. And you immediately have that. You put that into the second equation and you find that at a fixed point, I is got to be equals to sine phi. And this immediately permits us to see that if I is less than 1, in other words, you can have a solution for this equation where I equals to sine phi, you have two fixed points in the range 0 to 2 pi. Okay, I'll sketch what this looks like in a moment. But let's just go on with the possibilities. If I is greater than 1, then I equals to sine phi has no solution, and therefore you have no fixed points. So let's just plot it. It's normal. We plot the null lines. In other words, the y star equals to 0, and that is where phi prime is equals to 0. And the second one is the null line of I equals to sine phi plus alpha y. Okay, so here we have basically the null line y equals to I minus sine phi over alpha. We have that if I is greater than 1, there is no intersection between the two null lines, and you basically have no roots, but you have the two null lines. If I is less than 1, then you can see that this null line of y equals to 1 minus sine phi divided by alpha intersects the red null line at 2 points, which then corresponds to your fixed point. And we're going to name those two points respectively phi 1 star and phi 2 star. And you can see, because of the periodicity of sine, they're always in the range 0 to 2 pi. We then go on and work out what the linearized Jacobian is at these fixed points. You simply take it by taking the derivatives of our first order system. And here we have that it's 1 and minus cos phi star minus alpha is your full Jacobian. And you can then immediately do, as we've done often before, work out the trace, which is minus alpha, and therefore because alpha is positive by definition, the trace is always negative, so it's a stable fixed point if provided the determinant is positive. And we have that the determinant is equals to cos of phi star, and to evaluate that a little bit further, we're simply going to observe that at the fixed points, sine of phi star is equals to I. So it's very important to note that this, what I'm saying here, it only makes sense to write down A if I is less than 1. Okay, because otherwise there are no fixed points and there's no point in doing this analysis. So at the fixed points, we have that sine phi star is equals to I, and we can use this fact to evaluate actually what this determinant is in terms of the constants that are given. So we know, therefore, just using the sum of cos squared and sine squared, that cos squared of phi star is equals to 1 minus I squared, and we can therefore write down that the determinant is equals to plus minus the square root of 1 minus I squared. Okay, so we've now written our determinant in terms of the initial driving parameter. And we can see that the determinant is either positive or negative. So the one fixed point is a saddle if the determinant is negative. The other fixed point is either a stable node or a stable spiral, because the determinant is positive and the trace is negative. And to determine which one it is, we need to calculate what this combination of tau minus 4 delta is, and therefore we need to calculate this combination. Okay, so what we can see is that if alpha is large enough, then this thing is always positive, and then it is a stable node. Okay, and alpha, remember, refers to the amount of damping. So it makes sense. The more you damp the system, the quicker the oscillations disappear. Okay. Otherwise, it's a spiral. Okay, because that's the only two possibilities you have. Another thing to observe is that as I approaches minus 1 from below, in other words, as this blue line moves up until it just touches over there, right? So you still have fixed points in the situation, but the two fixed points are approaching each other. When that occurs, you always have that alpha squared is greater than 4 times the square root of 1 minus I squared, because this thing over here is getting very, very close to 0, and by definition alpha squared is positive. Okay, so in that event you have a node, and that means that the bifurcation that takes place as I approaches 1 from below is a saddle node bifurcation, which you can also see from this graph, right? This thing is moving up. Your two fixed points are going to, in some sense, annihilate and disappear. So it's your classical saddle node bifurcation. Okay, so we have already started getting a feel for our bifurcation diagram. We have a saddle node of bifurcation at I equals to 1, and we want to try and find out what other possibilities there are. Now, the interesting part begins if I is greater than 0. If I is greater than 0, remember we have no fixed points, because this null line up here is simply never intersects with other null lines, so you definitely have no fixed points. And we want to find a way of analyzing the system then and seeing what possibilities for dynamics are available. So we go back and we once again make use of the null lines to see what's possible. So let's do that. Here is the equations again, phi prime and y prime, just for reference purposes. We have alpha greater than 0 and I greater than 1. Okay, because we're looking specifically at the case where there are no fixed points. And so let's draw the null lines and see what we can say in spite of the fact that we have no fixed points. So we've done everything in the previous slide, what we could do with linearized analysis about fixed points, but we can actually say a lot more about the system. So this is the phi prime equals to 0, and unfortunately there's a typo, that should have been 3. So that's the one null line. Let's go ahead and just draw all the arrows on the null line. So at each point on this, where y is equals to 0, we're going to simply put the arrows in, and you can see when y equals to 0 and I is greater than 1, this thing is always positive, so all your arrows point up. Okay, so let's draw the second null line. And this is where y prime is equals to 0. So when y prime equals to 0, it simply is the change of whether the arrows point up or the arrows point down. And on the y prime equals to 0, the arrows are all horizontal. So we can draw them in at each point. We simply draw in our arrow and can evaluate how large the arrow is simply by noting that phi prime then is equals to y. So the higher the arrow is, or the larger y value, the larger the arrow is, but they all point to the right. Okay, they all point to in the increasing phi direction because y is positive. Okay, and just to get a complete picture, let's see what happens as we cross over this null line. So on the axis where phi is equal to 0, it's easy to evaluate. We can evaluate both phi prime, which is always positive, so it always points to the right, and we can evaluate y prime, which points up if it's below the null line and down if it's above the null line. So we can see how the field changes over here, but all of them point to the right. So in part, we are now basically trying to establish a trapping region. Another line we can draw is that another thing we can observe is that y prime is greater than 0 below the null line. The one example over here is what we did on the y equals to 0 line, which is always below the null line, that all the arrows point up. Even if you go for negative y, which we will not be considering further, they still point up. Okay, so taking this y equals to 0 line, you basically do have a trapping region. You have a point at which all the arrows are moving inward into this region. If you look at the upper half plane, once again, that's just reiterating what I say, phi prime is always positive. Okay, so the arrows are always going to be moving to the right. But above the null line, we have, in addition, that y prime is less than 0. So above this null line over here, you can see all the arrows basically point down. And so you can actually use this fact to establish a trapping region. Right, so you can take a trapping region that is just infinitesimally above the null line. You'll have all the arrows pointing down over this dotted line. And then you can do the same and have a line just below the null line. And then all the arrows will be pointing up. And you also have this particular line here at phi equals to 0, in which all the arrows always point to the right. So this thing is slightly different from the trapping regions that we have used in the past, because so far this domain is infinite. Okay, so we've just proven that we have this infinite strip where all the trajectories eventually enter, because everything above it is going to eventually come down into the strip. Everything below the strip will always move upwards until it's in the strip. Okay, so the claim we're going to make is that within the strip there is actually a limit cycle. Okay, so the claim is for I greater than 1, all solutions are attracted to a periodic orbit, and we now want to prove it, but we have to make allowance for the fact that we have an infinite trapping region over here, and we have to find a clever way of actually dealing with this. And it's this thinking that eventually led to the idea, or started laying the foundation of a Poincare map. So look at this analysis that's coming really, really carefully and try and understand in detail. They're all straightforward steps, but once they are eventually generalized, they become very, very powerful in subsequent explorations we'll make. Okay, so all I'm going to do is blow up this thing a little bit and just look at the region between 0 and 2 pi. And the reason I look at that is because there's nothing in the equations. It has a symmetry. If you replace phi plus 2 pi, the equations don't change. Okay, so you can quite easily identify this 2 pi back with 0. And this is entirely plausible or transparent if you're thinking about the pendulum, right? It's simply an angle. If you think about the Josephson junction, that is less obvious, but that's the power of having two physical situations that correspond to the same model, you can use your intuition from the pendulum to actually help interpret the results. So think of this thing as a pendulum, and phi is just the angle, and you can identify whatever happens with 2 pi back to 0. Okay, so this argument we're about to use to prove the existence of the periodic orbit in this infinite domain is only valid because you have this y equation is 2 pi periodic. Okay, so the argument for arguing that there is a periodic orbit is as follows. So let's imagine we start with y1, which at phi equals to 0 on the edge of the trapping region. So you can now see, and then we integrate the orbit. We don't even need to integrate the orbit exactly. We can sort of just look at the property, or we can sort of estimate what the orbit's going to do. So I'm actually going to plot the exact orbit, but you can actually see how you would draw this without knowing what the orbit is exactly. So if you start over here at y1, you know that everything below the null line, that a y prime is actually increasing over there. So the thing will move up, and it's always moving to the right. Okay, so there you go. You integrate the orbit, it moves up and to the right until it gets to this null line in y prime. At that point, it stops moving up and it moves horizontal, just as you expect from these arrows that you drew on the null line. So there it's horizontal, it always meets the null line with a sort of either inflection point or a maximum where the derivative is 0. Once it crosses the null line, you are now up here. Okay, so there the y component is actually going to decrease, but it's going to continue moving to the right. And that continues to happen until it once again hits the null line over here. When it hits the null line, it is moving exactly horizontally, so you can see it's sort of decreased. And then when it crosses the null line, you're once again in a regime where y prime increases. So from here, the curve is going to go up to that point, cross the null line, decrease, and eventually gets to 2 pi. Okay, so this is the exact orbit, but nothing that I drew here actually requires the exact orbit. It just can be gotten directly from the idea of how the arrows look that we sketched in the previous case. Let's now do the same thing, except that we start up here. Okay, so just one before I go on. The definition of this, the image of y1 after you've gone for 2 pi of phi, is something we're going to call p of y1. Okay, so this is just a definition, but we can view it as a function of y1 after you've traveled 2 pi and phi. Okay, so that's going to be the definition of what the function p does. Basically, p is the value of y1 at phi equals to 2 pi after you've integrated the equation. And the only thing we need to know about this is that p of y1 is greater than y1. Okay. And what we can do now is go back and do exactly the same thing with y2, where y2 is now chosen to be at the top edge of the trapping region. So let's do the same thing. We integrate it. We know that y prime is basically less than 0, so it's decreasing. So we move downward until we eventually hit the null line. We go across it horizontally. Then in this region, the arrows point up again, so we increase, okay, till we get to the next null line. We cross it, and then we decrease again. But now this is very important. From the uniqueness of the trajectories in the dynamical systems, the uniqueness theorem, we know that this top trajectory can never cross the bottom one. Okay. But anyway, let's just, before we go on, let's just call this image of y2, we're simply going to call it p of y2. And the only feature we need of it is that it's going to be in the trapping region and it's going to be less than y2. Okay, that's one of the features, because y2 is always above this null line, right? And y1 is below the null line, thus you never return to them because all the arrows across y2 are downward. Okay, so it's very sure that P of y2 is less than y2, P of y1 is greater than y1. Okay, and now it becomes interesting because of the identification of 2 pi with 0, you can go on and you can complete exactly the same thing. In fact, you can take this P of y1, translate it to this side, and treat it as a new y. So there we go. We've taken P of y1. We move it now we now treat it as a new starting value. And we can once again then integrate the trajectory. Okay. And we know that the trajectory will never cross any of the other trajectories. So let's see what happens. You integrate it. It increases. And because it can never cross these two trajectories, it's going to be, the final result is going to be between P of y2 and P of y1. The same thing you could do is you can take this P of y2 that we started with, put it on this side, and then once again integrate its trajectory, and it's going to remain between y2 and P of y1. So then we go on like that. And we eventually get another P over here, which we're going to call P of y2. And you can go on this way, and you can see that every time you take it from this side to that side, you're between the previous 2 points. So for example, once you've taken the end product of P of y2 and P of y1 over here, you to take it to this side, you lie between them. And you can go on with this until you get this unique orbit where y star is equals to P of y star, right? Because it's always sandwiched between the previous two orbits, and eventually you'll just get one orbit there. And that orbit, and in fact I've drawn it over there with dots. There we go. That orbit is what we will claim is the periodic orbit. Okay. So we basically start with 2 points on the edge of the trapping region. You work out the result after 2 pi. You have the property, the sole property that P of y2 is less than y2, P of y1 is greater than y1. You then take these 2 points, you move them to the right-hand side, and you repeat the exercise, and you can see because the trajectories don't cross each other, you'll eventually get this unique orbit y star, such as y star is equals to P of y star. And this map where you work out what P is after 2 pi increase in phi is something they call a Poincare map. Okay, so there we go. So if you were to take P of y star, move it to the right hand side and say it's the new y star, you would just be on your periodic trajectory. Okay, so we've claimed that we've shown that there is such a trajectory, and we now want to explore more of its properties. Okay, so we're going to start with the 2 features that we derived on the previous slide, simply that the image after 2 pi integration of y1 is greater than y1, and the image of a 2 pi integration of y2 is less than y2 if y2 is on the upper side of the trapping region. Sorry, on the upper side of the trapping region. And we can further claim that P of y is a continuous function of y, and that's easy to see because you can always define P of y. So pick a point y, integrate it 2 pi, and you find P of y, and it's a continuous function because the trajectories are unique and they don't cross. Okay, so using that, because it's a continuous function, the uniqueness theorem basically implies basically is a consequence that the trajectories don't cross. And what that also means is that P of y is monotonically increasing, right, because they don't cross. And this is only true within the trapping region. So what we have now, if we now go ahead and we plot P of y, namely the image of y after you've integrated it for 2 pi, versus the initial image you started with, you've got the following situation. You've got y1, you integrate it, you get P of y1, which is greater than y1, and you have y2, and you get P of y2, which is less than y2. Okay, so to sketch that, you can basically sketch the unique place where P of y is equals to y, and you know that y1, P of y1 must lie above it. Okay, so you have that P of y1 is greater than y1, and you're also going to have that P of y2 must lie below this line, P of y equals to y. And so the simplest way of having a continuous function P of y that is monotonically increasing is to draw a curve like this, and then you're assured that it is going to cross the line P of y at least once, which guarantees the existence of this very, very special solution where P of y is equals to y, which corresponds to your periodic orbit. Okay, so there's our periodic orbit, and we're guaranteed it. Okay, so using this very basic argument that P of y1 is greater than y1, P of y2 is greater than y2, and the properties of the solutions of ODEs, we can immediately show that there exists a y star such that P of y star is equals to y star. Okay, and as I mentioned earlier, P by definition is defined as a Poincare map of the system, and y star corresponds to the periodic orbit. And this basically is all that is necessary to prove that for I greater than 0, there exists at least one periodic orbit. But a reasonable question now is whether this periodic orbit is unique or what other possibilities exist. And to see why this is even a question, consider the following 3 cases. Okay, so suppose we have P of y, and we have this line P of y equals to y, and we want to explore what situations are possible if you only have the requirement that P of y1 must be greater than y1 and P of y2 must be greater than y2. Okay, so those are the only requirements you have proven so far. But it's possible to have a continuous monotonically increasing function that does this. Okay, you can see. So there are at least not 1, but 3 possible periodic orbits over there. Okay, so the important fact is, with these assumptions, we have not ruled out this possibility, and we'd like to do it because we'd like to show that the periodic orbit is unique. Okay, so it's just an example of, in some sense, tightening up our argument. Another example, so there are the 3 limit cycles, YA star, YB star, and YC star. Another example that we have is this case. Okay, so once again, let us satisfy these 2 criterion where P of y1 is greater than y1 and P of y2 is less than y2. Okay, so that's the criterion. You could do the following as well. You could have a monotonically increasing function that does the follows. It behaves as follows. Okay, so basically it increases, then it hits this line P of y, and it has more than a point of contact with a line. In other words, this would correspond to a whole series of fixed points all the way along there, which isn't really a unique periodic, well, it's several periodic orbits, sort of like an instantaneous center in a way. Okay, but the orbit obtained in this way is definitely not unique. So a reasonable question to ask is therefore, given that we've now proven the existence using this Poincare map of a periodic orbit, what is the nature of the periodic orbit, or are there more than one? Okay, and that is something that I will be addressing in the next lecture. Thank you very much.